Okay. I did the first presentation on the topic more than a year ago, working with King Cho here, my students. And now, since then, we made major progress on this research. So I can report more things then. So the topic is rather abstract, condensed. So I'm gonna use a more specific. All right. I use a specific problem to show how this theory works, what they is doing now, and what they can do in the future. In hydrology, one of the major process of variable work with the soil moisture. Soil moisture plays an essential role in many systems, many processes in hydrology, modern hydrology, including the fact the evaporation, the fact the surface energy, water cycle, the fact the ecosystem. So it's one of the most important processes in hydrology. And to measure the soil moisture on the global scale, we need to use satellite. So there are two missions to do the global measurements of soil moisture using satellite. One is the European version, one is the US version. So I'm using the example here is the US version of the measurement remote sensing for soil moisture. So this is called SMAP, called soil moisture active passive mission. So they use two L-band, so-called L-band radar and radiometer. L-band with a 1.4 gigahertz frequency to use measurements. These radar is used active signal to measure the reflection from the surface. Radiometers measure the passive signal from surface. And they use this frequency because this is most suitable for measuring soil moisture on the global scale. So the theory behind the L-band radiometer radar measurement of soil moisture is well reported, documented. I'm not going through that. I just show you one of the earlier products from the SMAP mission measures global soil moisture. It shows like this. You can certainly see with the color called is bluish, it's lower soil moisture, and bluish is higher soil moisture. You do see the global patterns of soil moisture from this measurement. So this is the background information about the theory we're going to talk about today. And the idea of doing this soil moisture measurement is there's a radiometer, or actually SMAP has both passive and active. Active is radar. Unfortunately, the radar failed 3 months into the launch in orbit. So we only have 3 months of radar data. And now the continuous record of passive radiometer data are available. So most of the so-called algorithm development from SMAP mission to retrieve soil moisture on a global scale is based on the radiometer, the passive signal from the surface. The basic method of soil moisture retrieval from the satellite is represented by so-called tau omega model. This is a simplified version of radiative transfer method. So basically it says there's an emission of radiation. As we know, everything in the universe emits radiation at all frequencies. So from the soil, it emits radiation. And we measure this radiation at 1.4 gigahertz frequency and the narrow band around it, so we can receive enough signal to use for data analysis. And so this is soil emitted radiation. They could reach the radiometer directly if there's nothing on the surface. But large part of the Earth's land surface is covered by vegetation. So that signal emitted from the soil has to go through the canopy. Then this radiation will interact with the canopy material. They will attenuate, they will scattering, they will reflect, all that. So there's a suite of process going on when the signal from the soil surface reaching the radiometer. That's what is needed. We want to get the emission from the soil surface. Then from the emission intensity or the radiation energy intensity, we can backtrack how much water in the soil. So that's the idea. But for the vegetated surface, there is the vegetation or canopy in between the surface and radiometer will interfere with the signal. So there's always the difficulty of say see through this vegetation so that the radiometer can see the soil. So we need to consider both the emission from the soil and the emission from the canopy. So the signal that the radiometer receives has two components. One is the emission from the soil, one is the emission from the canopy. So we need to separate these two to get the signal we want. We want the soil emission. Well, actually, we also it will be good to get the vegetation water content as well. So how much water in the plants. But the primary goal of SMAP is soil moisture. So anything beyond that is not their main focus. So then we can write the so-called radiating transfer process for the radiation emitted from soil to reach the radiometer. So that's the simplified representation of this radiating transfer equation that relate the surface so-called emissivity. That's what was needed. So the emissivity is characterize the surface condition so that see how different it is from black body radiation. So for black body radiation, we know from Planck's law, we can back calculate many other variables. But usually the material we see are not the black body. So the how not black, that's characterized by so-called emissivity. So emissivity ranges from 0 to 1. If there's 1, it's black body. If it's less than 1, it's not black body. So once we know the emissivity of the soil surface, we can use other method to retrieve soil moisture to figure out how much soil is, how much water in the soil. So the TB is what really measured by the radiometer, called the brightness temperature. It's not the temperature, it is the amount of radiation energy, flux, reaching the radiometer, represented by a temperature variable based on Planck's law, because over this frequency range and the intensity of radiation is proportional to temperature. So that's proportional, there's a coefficient in front of it, but the basic quantity is the temperature. So that together is what we call brightness temperature. So keep in mind, it is the energy, radiation energy flux that radiometer receives. The other variable, TS, is the surface temperature. Of course, we know black body radiation depends on temperature itself, physical temperature. It also depends on the radiation from vegetation, from canopy, depends on canopy temperature. So the temperature are important, the fundamental variables to characterize the radiation fluxes. And TV is the temperature of the canopy. And the ES emissivity, that's what we really want. And the radiation from the surface passing through canopy will attenuate. They will interact with the canopy material, will be absorbed. Part of the energy will be absorbed. So it becomes a heat. So the attenuation of the radiation from surface through the canopy is represented by so-called transmissivity. So how much radiation passing through, right? So that gamma is a number between 0 and 1. If it's 1, means they're all passing through. If 0, nothing passing through. So that gamma tells us how thick this canopy is, or how much water in the plants thinks water is a good absorber of radiation, especially at the microwave. Then yes, so omega is a single scattering albedo, so this is a parameter characterizing the scattering process or radiation going through canopy. So what we really need is the emissivity, yes. But if you look at the equation, if I only know measure the brightness temperature from the radiometer, also we know the temperature, I say surface temperature or canopy temperature from other sources. I want to solve for emissivity. But here we have two unknowns at least. From one equation, certainly you cannot get the unique solution. So currently this map uses so-called ancillary data. So they can get some estimation of the transmissivity of the canopy and to solve for emissivity. So they have to get this information called ancillary data from somewhere else. So they can solve for emissivity. All right. So the problem is that transmissivity is another unknown that is hard to obtain. Now the problem is presented to the team. The SNAP team is to how we work with vegetation cover to get the accurate retrieval of soil moisture. So now the SNAP developed the algorithm to work with that. Now their current algorithm is still in use as operational to give the soil moisture product. They update almost real time, or at least very quickly after the signal being received. So far, they can do the retrieval for so-called thin canopy. Thin canopy means the vegetation water content is measured how much water contained in the plant per unit area. For that, we call the VWC, vegetation water content. It's no more than 5 kilo per square meter. Well, if you look at this color bar, the color is, if it's a VWC greater than 5, it covers significant portion of land surface. That area we call the thick canopy. For thick canopy, the current retrieval gave an unreliable product of soil moisture. So that's the challenge I've been facing the SNAP team for a long time. So that's the motivation that we want to do something about it. We develop a new algorithm method allow us to somehow see through thick canopy and to get the soil moisture, good retrieval soil moisture everywhere. So that's the goal. So you can look at the map. That's really motivate this work. Well,
the VWC, the vegetation water content, how accurate are the estimates we have?
Now it's mostly empirical estimation based on LAI, something like that, measurement.
Okay.
There are few field measurements also. They can collect the plant, dry it out, see how much water.
I know, that's what I'm saying. There are many plants, many different.
Right. So the data is quite certain. Proof.
Okay.
So that's but we have some sense.
Okay.
For like the plant, like grass, how much water content in grass, like 1 kilo per square meter, maybe less.
Yeah.
How much water in tree in the forest?
Yeah.
That's about 10 usually.
So the different types of trees do not make a difference.
Yeah, they do differ. Right. They differ. But the point is, I think more than 1/3 of the land surface covered with so-called dense vegetation.
Yes.
So the VWC higher than 5 kilo per square meter. So for that area, it's difficult to use current algorithm to do soil moisture measure.
And also, if you take out the deserts, then we're left with a small, because the deserts, what the heck are we gonna do with the desert?
Yeah. But that's another, they could get wet when they have occasional rain. But that's what the algorithm works the best. Since there's a bare soil, the signal directly from soil. So they can do soil moisture retrieval. So that's the background information about this work. So I was thinking doing this a long time ago, but only find a way out only about 2 years ago to find the clue to propose this new method to do the soil moisture retrieval under any canopy cover or whatever the PWC is. So this theory I can tell you today is called maximum entropy production. I did this presentation of maximum entropy production theory many times here. You probably come too late to attend earlier presentations, but in a different context. That was used for modeling surface heat fluxes. I'm going to touch a little bit here. That being published more than 10 years ago. Now it's more and more used. And they applied to land surface modeling surface heat fluxes, and they found this work very well. So very briefly, I cannot get into detail of the theory maximum entropy production. It takes at least 2 seminar talks to discuss in more detail. Basically, it's so-called inference at the very fundamental level. It's an inference algorithm for the system that we don't have complete information. We want to do a statistical analysis, say, to be sure to describe this what theory about. But again, at least this what's the theory is about. So what component the theory has. So it's based on so-called Bayesian probability theory. So the Bayesian probability theory, you may heard of it, you may not, but it is the so-called calculus inductive logic. So when we do logic reasoning, there are 2 types. We do deductive, that's what we're very familiar with. To do derivation, it's a deductive logic. And the inductive logic is based on limited knowledge and to make a guess of the proposition that we study to see which one is more likely to be true, things like that. So essentially, it's about hypothesis test, but really the hypothesis test versus the traditional statistics that which is mostly about the likelihood test. So let's put it short. And this probability theory is also the quantification of the probability we use the information theory. Basically, we use the concept information entropy, which is a concept very familiar to people now, used widely in statistical analysis. So then there's a so-called maximum entropy principle as a method, also as rules of assigning probability distribution based on available information. So this is also well known in science and engineering. It started from the statistical mechanics back in 1950s. So this is very familiar with. And then later, this maximum entropy principle understood as a rules, a principle assigned probability distribution being applied to study the non-equilibrium thermodynamic system to study the structure of thermodynamic system. So that application to the non-equilibrium thermodynamic system is often referred to as so-called maximum entropy production. I want to remind you, this name are really bad. It's often misleading. Things you may think of something, they may lead you to think of something else. Really, if you want to get the precise understanding what they really means, you want to look at them carefully to see. I don't have time to get into that, but just let you know what is the theory is built on. Okay, let's get into this quickly, the maximum entropy production theory in the context of non-equilibrium system. Basically, it says the non-equilibrium system so will correspond certain configuration of fluxes. Let's look at the energy flux, heat flux system. So this configuration of fluxes will be such that they will minimize dissipation function under constraint on conservation. This is a special case. So that's, yeah.
Can you make a simple example of what is an equilibrium system and
Yeah.
out of equilibrium system?
Equilibrium means there's a no transfer process.
Like, for example, if you put a knot of ice,
Well, that's not equilibrium. So you transfer heat, transfer mass, transfer momentum, transfer anything.
it's out of equilibrium.
Yes.
But you can still define an entropy.
Yeah, entropy that's why the entropy in the context of a Bayesian probability is a general description of the information, completeness of information. So it doesn't matter what the system.
But if you will consider a block of ice and the environment,
Mhm.
the system for a while will be out of equilibrium because there will be,
Yeah. Mhm.
and the entropy of the entire system will always grow, no? Because
Well,
no,
it's a
this
long
is the,
story. I will, well, it takes a long time to
Okay.
discuss that. But the entropy I'm talking about here at fundamental level is information entropy. So
oh,
this information entropy has some relationship with the thermodynamic entropy we're familiar with.
yeah,
So for the equilibrium system, that information entropy has been shown to be equivalent to the thermodynamic entropy.
Mhm.
But out of the equilibrium system condition, they are not the same. Things actually in the classical thermodynamics, there's no definition of entropy for non-equilibrium system.
yes.
So that's the difference. But this is the information entropy is such a general concept. It applies to any system as long as you have a probability distribution. So the information entropy is defined based on probability distribution. So that's a quick explanation to that. All right. So this is what you can think of the heat transfer process in this case to get a sense what this maximum entropy production theory is about. It applies to many other systems as well. To get into what we're gonna discuss today, I used the Ohm's law for conductor to show you what this maximum entropy theory can do to explain the Ohm's law that we're all familiar with. So the Ohm's law in electrical engineering is a very well-known physical law that we use every day, right? I can show you this Ohm's law is a voltage equal to resistance times the current. That expression can be represented in different manners. So that different representations of the Ohm's law actually is related to the maximum entropy production theory. There has two representations. One is called the principle of minimum dissipation. One is called maximum entropy production. They are two sides of same coin. I'll show you next what I mean. All right, let's see what the Ohm's law can be represented using the principle of minimum dissipation. So as we know, we use the two parallel resistor connect this way, and we have a current I0 go into these two resistors. The question is, what's the current of individual resistor passing through? Given we know the total resistor, the total the resistance impedance of the two resistors. The question, well, I know the Ohm's law. If I know the voltage, I know the impedance, I can calculate the current. So it's so simple. But now I use the principle of minimum dissipation to get that result. So we formulate the thermal dissipation. As we know, when the current goes through a resistor, it produces heat, right? The amount of heat is equal to the current square times the impedance. That's the so-called total dissipation of produced by the two resistors. All right, now I know the total current. I want to find the individual current. So I can find the minimize the dissipation function given the total current is fixed. So you can do that easily using the Lagrange multiplier method to get the minimum value of under the constraint. You find out that condition to have a minimum dissipation is exactly Ohm's law. And that actually, I didn't show the details. That Lagrange multiplier used to solve a constraint minimization problem is voltage. So it has a physical meaning of the mathematical solution. Then this is exactly Ohm's law. So Ohm's law, you could understand as the minimized dissipation configuration of the electric current. So that has this meaning actually. Then you can look at the total dissipation, and you know, oh, the total dissipation, the heat produced by the two resistors is just equal to the total current squared divided by the conductance, sum of conductance. So that expression is quite general. If you look at any configuration of electric circuit, they have the same expression. So this is the one representation of the minimum dissipation principle. Well, you could represent this process in different way. So if you write entropy production here, at current divided by temperature, that's the usual expression for the thermodynamic entropy, right?
Is it correct, the thermodynamic entropy?
Yes, yeah, the current divided by temperature, or P divided by temperature. So you take the derivative, you get the flux divided by temperature. So that's the general expression of thermodynamic entropy production. So that's the way. Assuming they have the same temperature, they say, it's a special case. Then you could solve given the dissipation. So I know the total dissipation. I see what the partition of the current. That gave the maximum entropy production. So, right. So that the total dissipation, even though I do not know the total dissipation yet, but I assume given the total dissipation, how the current is split between two resistors. Then you solve for that, you get exactly the same Ohm's law. That means Ohm's law can also be understood as the system correspond to maximum entropy production.
And what about the total current constraint? It doesn't.
It's there. It's a current. No, this is you can see this is a one question, two different ways, same question. Like given the constraint, you optimize the so-called object function.
Yeah, but you can also impose another constraint, E1 plus E2 equal I0.
That's the previous one. So this.
Oh no, you can even do it here.
Yeah, well,
the second one.
The second one is.
You can also impose another constraint, no?
No, you cannot.
Why not?
No. Well, that's what this leads to the correct answer.
Oh, I see.
Yeah. So if you, given in the previous case, we want to extremize the dissipation. That constraint is total, you can think of it as conservation law, conservation of energy. Here is opposite. Given the dissipation, what is the energy itself? So that's a different way of, you switch the constraint and the object function. So actually this is two, you can call it the
It's a dual.
right.
Yeah.
It's a dual conjugate problem. So they are equivalent, it's the same thing actually. So that's a two different representation of the same Ohm's law. So that's the
So actually, we can replace the current with the water fluxes,
yes.
volume flux into a pipe.
Yeah.
And then we can replace R1 and R2 to be
To
the
something to
inverse of the
conductance or resistance, whatever, yes.
from and then the potential to be the difference in height.
Yeah.
And so that basically, for a pipe system, we would have Q divided by temperature.
Yeah,
Water
temperature is
flux.
something here, arbitrary thing. It's not important.
Yeah, because you can you multiply by a constant to
Yeah,
make it
doesn't
any
change anything,
as long as it's an entropy dimension, no? So
Right.
it's
So here, the maximum entropy equivalent correspond to total energy.
No, but in a pipe flow, can we say that the heat generated, the heat flux is proportional to the water fluxes, to the volume fluxes?
I don't know, but some.
Because that would be the
I
analogy.
know, maybe 30 years ago, a student at MIT did that flow, to the flow. They could say this is, can be explained the same principle. So one of the application of the theory earlier is to study the energy balance of land surface. So they say that radiation is partitioned into three fluxes: latent, sensible, ground heat flux. Now we use the same idea to formulate so-called dissipation. So, but that dissipation function is formulated that way, put in the blue color expression. So it's a flux squared divided by some parameter. Actually, it turns out to be the thermal inertia associated heat transfer process. Then we can solve for the constraint, the minimization under the conservation of energy, and then we solve the heat flux. So that's the so-called MEP model of heat fluxes reported long ago. So that's the one application, not to radiation transfer, but for heat transfer process. Actually, I did the first, and then I started thinking about, can we generalize this idea to the radiative transfer? I didn't know how to do that because I do not know how to formulate something called the thermal inertia. So for radiative transfer process, so that's the barrier of doing that. I only figured out about 2 years ago how to do that. So now, this is Ohm's law can be interpreted as a principle of minimum dissipation or maximum entropy production. I want to generalize that to the Ohm's law to dielectric material. So Ohm's law is for conductor. Now we want to generalize to non-conductor, which is called dielectric. Everything else, I mean, is dielectric, so non-conductor. So that's what do we need to study the radiative transfer through soil, through vegetation, through other natural material. So for the remote sensing. So I'm gonna use the principle of minimum dissipation form to represent this theory. So the key is to introduce a parameter called the inertia, corresponding an analogy of the heat transfer. The thermal inertia is a well-defined parameter for material, right? But for the radiative transfer, it's not well-defined. There's no such thing called a radiative inertia. Things for the heat transfer is a gradient, right? Down gradient transfer. So the inertia can be related to the heat thermal conductivity or diffusivity, that kind of parameter well-defined. But the radiative transfer is not gradient based. There's no such thing as a gradient of something, so you transfer radiation. So we cannot get this radiative conductivity or radiative diffusivity, at least not directly from what I know. Although there is such thing as conductivity of material, but I'm not sure that's the one we need here. But here, we have to use analogy to formulate the so-called radiative inertia in order to formulate so-called dissipation function. So that's, and well, yeah. So the radiative inertia turned out to can be parameterized this way. The key is radiative diffusivity. So radiative diffusivity is not related to some gradient of electrical or magnetic field. It's not that. It's related to so-called penetration depth of electromagnetic wave in the material. Since diffusivity has a dimension of distance and time squared. So we need to get the length scale and the time scale. So the length scale in that diffusivity parameter here actually turned out to be the penetration depth of waves in electric material. So that is a well-defined constant. Yes, it depends. Oh, sorry. It depends on what? Depends on so-called complex dielectric constant. Dielectric constant is a material property of dielectrics. It has a real power, imaginary power in this way. So which is well known. So from there, we can calculate the penetration depth of the EM wave in this material. So that gave us a length scale. Then use that in that formulation, the optimization of so-called radiative diffusivity, then used to formulate the radiative inertia in an analogous way to the thermal inertia. So they have this correspondence. So then we used all this theory, this idea, this concept to formulate the, so we go back to our problem here. Now, I want to, just like in the land surface heat flux problem, we want to partition the net radiation in different fluxes. Here, we have a total radiative heat flux from the radiometer, which is represented by the brightness temperature. I want to partition this to two sources. One is from the soil, one is from the vegetation. So actually, the terms associated with the surface temperature is the soil source, the radiation. The terms associated with the vegetation temperature is that emitted from the plant, from vegetation. So we want to separate them, to partition to just like similar way as we do the net radiation partition into sensible latent ground heat flux. So that's we use this constraint that we use. Then use the formulated dissipation function. Let's see here. Yeah, so this is the dissipation function based on the Ohm's law representation. So here, the electrical conductance correspond to the radiative diffusivity, in the same way as the Ohm's law for conductor. And then we could solve for the same mathematical problem to get each of the fluxes, radiative fluxes emitted from soil and that from the plant. So that we get two equations. Actually, we have two unknowns. One is the emissivity of soil. One is the transmissivity of the plant. It tells how much water is in plant. So that's what the.
Can I ask you?
Yeah.
The split, the optimal split is 1 plus sigma, 1 plus 1 over sigma. Is this the harmonic series? Is the harmonic mean?
From the solution from.
I don't know, but is an harmonic mean?
What do you mean?
Harmonic, no, is when basically it's proportional to the inverse of the sums.
It's essentially it's that.
Is the harmonic mean?
Yeah, it is that. Yeah, harmonic mean.
That's how it's called. It's proportional to the inverse.
It's that.
So you can define 1 over something plus 1 over something.
Just the total impedance is 1 over individual impedance inverse, right? So the harmonic mean, it's like,
This harmonic mean shows up everywhere.
Yeah, exactly. So actually, you either as dramatic mean, right, or as a harmonic mean. One associated with just sum of terms. One associated with a product of terms, right? Then you take a logarithm and come.
Yes.
So it's the equivalent, same thing. So then we can solve the problem of the both emission from the soil and emission from the plant. We can figure out how much the radiation attenuates through the plant. It tells how much water content in the plant. And also from surface emissivity, we can figure out how much soil water in the soil, which is soil moisture. That's what they All right, so we solve for that based on the expression of this tau omega expression. We can find this analytical solution of emissivity and the transmissivity of plant. From this two, it's only function of TB, which is measured brightness temperature from the radiometer, and the physical temperature of the surface. And everything else is a physical parameter known as a priori. So we can solve for that. So this is called the MEP algorithm for canopy transmissivity and soil emissivity. And then from the existing algorithm of this map, we can relate to get soil moisture based on the emissivity. They have a well-developed algorithm to do that based on soil typing. That's the way to do it. All right, I'll just show you quickly the example. So the top panel shows the comparison of the physical temperature of surface with the brightness temperature. So brightness temperature certainly is lower because emissivity always lower than 1, less than 1. So the brightness temperature is always lower than the physical temperature. So that over Amazon, this is over the Amazon region. And this has over 3 years, who did that analysis. There's pretty flat because of in Amazon tropics, they're very weak seasonality. So that's shown. But the second one is a different location in the US, in the Missouri. You see more of a seasonal cycle because we're in temperate zone, not in the tropics. So the third side also in New Hampshire is even north. So as a similar seasonality as the second side in the temperate forest. They are all forested area. So I want to test that theory, whether it works. So this is what we get. Soil moisture retrieval, the top one. You can compare the new retrieval based on this method, MEP method in the red. The SMAP retrieval over this region is really bad. Everyone knows that. So it's on top, it's greatly overestimated. It's almost saturated to 0.6. It's close to the porosity, actually it's not the case. And they have a limited field measurement and it's isolated location. That's in the black, that's the field measurement. So we can get that consistent with the field measurement. At least the bias is much.
So the stars are the actual measurements from, or the estimates from the SMAP satellite.
Yeah.
While the black ones,
yeah.
the ones, so that's a significant bias.
Yeah.
But that's for the tropics. For the, yeah, and so for the
vegetated, yeah, we're looking at the vegetated region, so that's the goal. So you want to to get the.
So one of your lessons is that don't use SMAP for vegetated surfaces.
They do retrieval, but they tell you, well, this is as large uncertainty. Uncertainty is not very large. Yeah, the big bias, very large biases.
So there is a periodicity in the estimates of SMAP and MAP, which is not reflected in the in situ measurements.
Well, in the in situ measurement, there is some seasonality.
But they don't seem to correlate.
They do correlate. They do correlate.
I mean, in the top, the red and the yellow, they don't have the same periodicity.
No, well, the things, the field measurement is short. It's only, within a season. So you don't see much seasonal variation that, it is a tropic, so.
No, I'm talking about the yellow data.
Oh, that's the precipitation.
That's the precipitation. It has nothing to, okay. So what are the in situ measurements? Where are they?
The black.
Show the limited black.
Oh, okay. I thought they were the yellow.
No. The limited black, we just show the precipitation just as a reference.
Oh, no, okay, yeah, you got a good agreement. Yeah. I mean, it's a good.
At least the bias
is reduced.
So that's important.
Yeah.
There's always a scale issue. So we look at the remote sensing as over this grid size at 9 kilometers. Well, you compare with the point measurement, it's always.
And SMAP is based on what? On regression models? I mean.
No. They have their retrieval algorithm.
They have their own retrieval.
Based on the radiative transfer theory.
Okay. But it's not, it's not optimized.
It is optimized. Yeah, they are optimized. They're the big team to work on it.
Yeah, good job.
Yeah, so, but they from their current method of retrieval, they do have difficulties work with a dense canopy, with a high vegetation. So they believe this attenuation of the radiation from surface through canopy is higher than they actually is. That's based on their current algorithm.
So did you do it for the entire globe?
Yes. Yeah.
Do you have the map? The new map?
I have it, but we don't show it here. I'll show it here. And then we compare to other two sites. They also show better performance than the current SMAP data product, and we compare with it. So it's quite.
So basically, it is a simple harmonic mean.
Yeah. Well.
And it gives you a better.
Yes. The thing is, I think this way we know better the radiative transfer process. then I think you look at this, it doesn't have any empirical parameter or functions or into that. But in the existing retrieval algorithm, they have a lot of that.
Yes.
They have a lot of that.
Jingfeng,
Yeah.
can I ask you, the biases, okay, there are large biases, but do they have a pattern? I mean, for example, why do the biases, sometimes the biases are high, sometimes the biases are low. Do we know, is there a study that says that, you know, when in the morning, whatever, the bias is high?
Yeah, Google can tell you about that. The bias is there.
So that we can, you know, that information, although it's biased, could have interesting and useful information in it. So the question is if there's a pattern that we can see.
Basically, they overestimate so-called optical depth of the plant.
Of the plant.
So they think that the optical is optically thick, thicker than it really is. Because they use an empirical relation.
I understand that, but I'm saying, why does it go up and down? You know, especially for the upper part, the Amazon, it doesn't change very much from day to day, from year to year, month to month. Why the biases change?
The bias?
I mean, the bias, the estimation of the, you see.
Oh, you see a lot of fluctuation, right?
So I'm saying, is there any relationship with the bias? Because if there was, we can extract these biases and the smart data could be.
I'm not sure what causes those fluctuation noise in their estimation.
The atmospheric.
Well, usually it's not atmospheric effect because this is the L band. The L band frequency, the wavelength is very long, 21 centimeters.
So it goes to the clouds.
They go through, they go through it. It's not a problem with that.
That's interesting. Why?
They have that property. There's many issues to do the retrieval. The scale is one. So they look at the grid scale. The grid scale process, including many other things, so it cannot be resolved.
Did they ever manage to fix the satellite? Remember, there was a glitch.
Oh, the radar thing. No, they never fixed the radar.
Yeah, so
Radar failed 3 months into the launch and never coming back. I think they tried, but they couldn't get it back to work. So there's no radar measurement signal, only the passive signal.
Yeah.
And the European version of this version does not have radar. It's only passive radiometer.
Yes.
So now there's no L-band space flowing radar for soil moisture retrieval for now. L-band.
Yeah. Okay. Yeah. All right.
So then we at the same time we can retrieve the soil moisture. This is a retrieval of the vegetation water content from this as a simultaneous retrieval. Well, in the current SMAP algorithm, it has to be coming from somewhere else. It's not from their retrieval. So they call it ancillary data, supplementary data from somewhere else. But we can do the retrieval of soil moisture and the water, soil water and the vegetation water at the same time. So we got simultaneous retrieval. So that was compared with, well, this is a different location. This location, the vegetation water content usually is lower than the tropical forest. So their retrieval should be reasonable. I think so. So then we have the retrieval. I just show here, it not only retrieves soil moisture, but also retrieve vegetation water content, not only for the forest, but also for the lower water content area. So it works everywhere.
So basically, when you have when a system is in series, the fluxes they basically split with the regular average. Here instead, because we get this harmonic mean, it means that the two fluxes it's like if we have two systems in parallel, and because that's when you're gonna get to the harmonic mean. So what is what are the two parallel systems here?
It means the flux tend to go through the path with less resistance.
But basically, the prediction, it looks to me that you have the soil and the canopy, but they are kind of the analog of two systems in parallel.
Yeah, in parallel. Yeah.
Although physically, it looks like the energy transfer should be more like a system in series.
This is the two source. So we want to split the total energy into different sources.
Okay.
It's a summation. Summation means parallel,
parallel.
yeah.
But physically, they're
Current-
not in parallel. Physically, no,
Yeah, parallel in terms of superposition of.
yeah,
all
that's
the-
why you get the harmonic mean, basically.
Yeah.
So it's,
Mhm, yeah. So that's the,
So the blue, the red again is what?
the blue is what blue is the SMAP product.
Okay, and the red is
Red is with new retrieval based on this retrieval.
based on the stuff you do.
Yeah, right. So, yeah, certainly they agree and they have the same seasonality at least. But sometimes they give a different amount of the vegetation water content over the area. But at least they're
So the
Following
seasonality is obvious, I mean.
seasonality is obvious.
Yes.
can I ask you now, if the two systems are in parallel, does it mean that their radiation are completely independent? Or they interfere?
They interfere, but this is the what this theory can do. They can separate it.
Hmm.
They have to be in such a way, if that's correct, so that the total dissipation
Yeah.
is minimized.
I guess what, if I understand what you were asking,
Mm.
is the emissivity, the radiation that comes out of the soil, as it goes to the canopy and emerges at the top of the canopy, is it affected by the canopy?
Yeah, it
And then
does.
you have the canopy
Yeah, they
radiation, right?
include that effect is included.
Included,
Yeah.
okay,
So the emission from soil
yeah.
will absorb by vegetation and emit from that thing again.
Mm.
Then
And then you have the emission from the
from vegetation, there were part of the emission from vegetation were directly out.
go up.
Part of it will go down
Yeah.
and reflect, and then
Yeah,
attenuation again.
yeah.
Then also for sometimes there's a radiation from surface and from it will be scattered, not only absorbed, they have scattering.
That's what make them parallel, make them
No,
like
that's
parallel
nothing to do with that. That's about how much energy is lost.
Okay.
How much radiation energy is lost into heat. So that's actually essentially tell us how much radiation energy is lost when it transfers through material. You can think of it as an interaction of electromagnetic wave with the material.
Yes, what I'm trying to say that from your, for the maximum entropy principle, is telling you that your physical system is equivalent to a parallel system. Which are
Well,
connected.
In this way, you can interpret this way.
Yeah, it's an
Yeah,
equivalent system.
yeah.
So I was trying to understand, what is this
What-
equivalent physical system,
Yeah, this is
What
more.
happened to, because I mean, that's what happened. I mean, if, it works well, and so the parallel system has to have some physical
If you
meaning.
think about the total, something has an individual component. You want to fund from the total to individual one. So this is the parallel. Right?
Yes, exactly.
And of course, the emissivity of the soil depends on the soil properties.
Yes. Soil property, most part of the soil moisture.
The 5 centimeters.
Yeah,
of-
actually, they found out they can be deeper than
Yeah,
that.
and it has water too. The water
Right.
in the soil affects that.
Yeah,
So the dryness.
exactly.
That's right.
Yeah. I'm actually already working on that to separate it from emission from the soil moisture, emission from dry soil.
It's
They can be
yeah.
separate.
Okay, I'll talk
Yeah.
to you later.
Yeah, so that can be done from just the start of this idea to do that. And so that's what we can see. I think we can solve the retrieval problem over dense canopy covered regions. But there's more about this new theory for the remote sensing. So first of all, this theory or this method, this is formulation what we developed here applies to all EM waves at all frequency. So we do not specify frequency in there at all. You just the measurement of brightness temperature. That brightness temperature can be any frequency, not only the microwave, but any. This is radiation energy flux to partition from different sources. So that's what they did. So this is, in theory, applies to all remote sensing problem and all frequency. And you can do single channel, single frequency, and single polarization. So individual one. So that treats all the retrieval problem actually in the same way. Okay? So doesn't matter what surface is, maybe plant, maybe soil, maybe water, maybe snow, maybe ice, whatever it is. This is That's the, apply this theory to remote sensing of the Earth system in the same way, or for any process, you can formulate in this, then there's no, any, empiricism or any empirical equation parameter to use. Certainly there's no tuning parameter, nothing to tune it. It's all everything there, including the algorithm, is a physical parameter. So if you know the physical property of this material, so you don't need to.
So basically, the way SMAP does the splitting,
Yes.
basically is they are overestimating the dissipation. The dissipation.
I think they overestimate the optical depth of water implant.
No, what I'm trying to tell you, if your minimum is a true global minimum, is right when you do the calculation.
It's, in this case, it's local and global.
And yeah, so if you when you do the average, imagine you do a mismatch, you add a misfit in your formula down there, you put a plus epsilon. So you want to see if you alter the.
This is the global.
I know. But so what does it mean that if you don't do a perfect harmonic mean, but it's going to be an imperfect harmonic mean, this estimate they're going to be overestimated. Basically, they will tend to SMAP.
Well, they use a different algorithm. They use a different. They only look at the.
For example, imagine that you split it half and half. What happened to your estimate? They will overestimate the data, or will
I don't know.
down estimate?
I don't know. I haven't looked at that. I don't know if you look different partition, it give you what it is. Yeah. I don't think you're gonna get correct.
No, but you're gonna get customers map. You will always overestimate.
Oh, you mean, I don't know if that the new, based on what you said, it's overestimate, underestimate. I don't know.
Okay.
It's not useful right now, this map with this kind of.
No. Yeah, I was trying to understand, where SMAP is,
It's
in
over
terms.
for the vegetated surface.
No, in respect to his MEP approach.
Yeah, it's.
So, because
Overestimates, that's all.
so you have a global minimum. You got your system is here. SMAP, where is going to be on this side or on this other side?
Oh, I have no idea. Probably
Higher.
higher. The right side is
Yeah,
higher.
sure. Yeah.
I don't know
The
about
question is
that.
how, yeah, then, because that, the theory can also help to measure the error of these other estimates of this other
Well,
and correct them.
I didn't show the error analysis. Well, it's easy because we have an analytical expression. They easily look at
So
each contribution, each component.
there is one, the way to do this is typically in other cases where the same problem arises in other situations. The way I have thought to do that is to try to figure out, are the signals different between the emissivity from the canopy versus the emissivity from the soil? And the signals are different.
Yeah, it
And
is.
the reason they're different is because the photosynthesis, during
Yes.
the daytime, those darn things are doing nothing.
Of course, yes.
The WV
the
is
signal-
changing,
Absolutely.
while the soil does not.
Yeah.
See what I'm saying? So there must be a way to figure out what the difference is in this emissivity. You see what I'm saying? The radiation signal is different because of the different process that we have to go
Yeah.
through. So you can, that's how
I
to
agree,
separate the two.
But that's the point. This theory allows to separate these two signals based on this principle.
That's all. That's good. That's the way. So based on the physical process.
Yeah.
And since I'm asking one question, one observation. Another way that I would say, imagine a case where we have, let's assume that we're in Brazil or somewhere. So you have this problem with the biases, but then there is this logger companies that they have actually shaved and there's no, so the spatial difference between the radiation that comes out of the place where there's no canopy versus this can be used to separate the two.
Absolutely.
Have you done
Absolutely,
that?
yeah.
That to me is the best.
I think
probably.
we look at the area where the surface has a lot of water.
Yeah,
Yeah.
the water, yes.
Yeah. Then you're gonna see
The difference.
signal, certainly reflect that. So
That's right.
in that case, the brightness temperature is very low.
Yeah.
Because the water brightness temperature is low. So you see that that the signal is very clearly.
So then you can find the soil emissivity and radiation, and then you can actually figure out what the canopy is.
Yes,
That's,
yeah,
that's the way to do it. So it has to be like a spatial kind of comparison.
exactly,
Yeah,
yes.
Just not point by point, right?
Well, there's always the issue of scale.
Yeah,
So we look at actually the original resolution of the radiometer is a 40 kilometer.
40, that's a big.
Oh.
It's big, so they can cover a lot of things, right?
Yeah.
So, yeah,
Don't they go down to 9 by 9?
now they downscale to 9 by 9, but still that's something, they have to use some, also supplementary data based on vegetation cover, which usually have a higher resolution.
Right.
They can separate them, so to get the finer result, but that's a process data, not the original signal. Original signal still is the 40 kilometer, TB. So whether you can split in 9 kilometers post processing, but the information of a 9 kilometer resolution actually is not there.
And the same thing, the same problem we have with the smart when there's snow of different depth.
Yes, we're looking.
We're looking at that.
We're working on snow now. Usually, people don't believe L-bank is used for snow retrieval. We just tried. I think it's possible.
So basically, SMAP gave you funding to screw them?
No. This is
I'm just
not,
kidding, no,
this is
but-
not the funding what the project is about. It's about something else.
Oh, okay.
On the way, I just figured that out.
I mean, I don't think they are so happy about.
I think they will. Things that will make their, the mission as something new.
Oh,
They will improve their data quality. Why don't
with
they?
this approach.
Why? Yeah.
Okay, they put it, okay.
So they can improve their product.
No, so I mean, but I mean, don't tend to be hilarious, but.
No. Well, you don't, I guess any scientist will be happy to see advance, not because,
Unless they have a ego,
everyone does, but,
Are we in the question session? Can I ask one more
Yeah.
question?
Yes.
I have to go. So.
Where's the pizza?
No, that's not my question. So, I was thinking of what you said, it's a dual, it's a fundamental question.
Yeah.
So, I was thinking of, there are two approaches, of course, the dissipation, minimization, and the maximization of entropy.
Mhm.
These two, they are dual of each other, but one of them may be better than the other in certain applications.
Well,
Do you have
Sure.
something to say about that?
I think they are equivalent.
They're equivalent in terms of the final thing, but for example, in the case of this, some of the data, they require different data, right?
Exactly, that's the
And
point.
the data that they require may be less accurate in the dissipation fluxes versus the maximization of entropy.
It depends on what you know.
That's right. Depends on the data we have.
Yeah. But usually the rising temperature data is what we have.
Yeah,
And dissipation data we do not have.
we do not have, that's right, it's a fluxes problem, it's the
Yeah.
same thing.
Yeah.
So I'm
Exactly.
saying that depending on the problem we have.
Exactly.
we should
Depends on
understand.
what available information, you choose the representation of the same principle.
It's a very interesting problem.
Yeah.
Thank you.
Any questions from the audience?
Audience,
Or from our virtual friend? Any questions? If not, let's go to SEB building in the lobby. Do you know what it is? And there will be 9 pizzas, okay? Thank you.
okay, thank you. All right.
Okay, let's go. Thank you, very beautiful.
All right.
I need to learn more about this.
Okay. All right, we can talk about that.
Yeah.
Okay.